Start the screen. Okay, so hello everyone and welcome to the Thursday Colloquium. I'm really pleased to announce we've got Jamie Vicary here today talking about understanding free infinity categories. You all have permission to unmute yourselves, so if you have any questions, feel free to unmute yourself. There'll still be a question time at the end, but feel free to interrupt. And if you want to direct message me a question, then I can always read that out as well, or you can type in the chat or whatever you like. So Jamie, whenever you're ready.
Thanks, Tim. Hi, everyone. It's great to be here at this really nice seminar series. I'm amazed there's so many people interested in free infinity categories. Okay. This is the way I'm going to talk about this. This is joint work with Christine, Eric Finster, Ioannis, Markakis, and David Reutter. And the way I'm going to talk about this and this topic itself, it sort of falls nicely between computer science and mathematics. So maybe there are people here representing those different sort of approaches. So if you feel I'm saying something in a way that like I'm not using the words that you like to use, then please stop me and we can have a discussion and try and develop a vocabulary that makes sense to everybody. Right, what's going on? Okay, so let's start with somebody who will be known to most people here, I suspect, Alexander Grothendieck, who of course died quite recently, very sadly. There's lots of nice photos of him online. It's a nice one. So most people here will know a lot about him, so we won't dwell on him for a long time, but he had such a strong personality, and I think the personality actually affects this work I'm going to talk about in a certain way. So let's talk about him briefly. Creator of modern algebraic geometry. He got a Fields Medal, and some nice things were written about him, particularly in his obituary. His unique skill was to eliminate all unnecessary hypotheses and burrow into an area so deeply that its inner pattern reveals themselves. He was considered by many the greatest mathematician of the 20th century. That's a nice thing. I wouldn't mind it if someone would say that about me. Probably unlikely. Anyway, especially the last bit. I was sort of looking at the first bit when I said that. So we're going to look today at some ideas he had about the theory of infinity categories, and I think that these ideas of his we're going to explore fits this quotation really, really nicely. You can tell me what you think of that. He felt his insights were not always well received. However, he was very concerned with foundational questions. I feel like he would be very much interested in the sort of, if he were 30 years younger, interested in the sorts of questions in the foundations of computer science and mathematics that we think about it in this community. And here's a nice quote from him: "A wind of disrepute for any foundational matters is blowing nowadays. I don't know if we feel that wind still blows the same way or not." Not one picture of Grothendieck, but two. And Andy Pitts, when I showed him these photos, he noticed that Grothendieck's wearing the same belt in both photographs. It's kind of, I like that. Tells you something about his personality, but maybe you don't want to read too much into it. So Grothendieck was obsessed with finding an axiomatic system for well-behaved topological spaces. So he really, I'm sure he appreciated paradoxes like Banach-Tarski, which will be, I'm sure, well known to many people here, where you can take two balls and take one ball and rearrange the points and obtain two balls identical to the original, which seems possible until you realize that the one ball and two balls have the same cardinality of points. So of course, Grothendieck, I'm sure, respected those sorts of results, but he wanted an algebraic theory for dealing with so-called well-behaved topological spaces, which would rule out paradoxical behavior of that kind. He didn't think that mathematics was wrong, it just wasn't mathematics he wanted to do, perhaps. And so he wrote in connection to this. One thing which strikes me is the absence of proper foundations for topology itself. Something that many people today in the foundations of mathematics, computer science, would probably say that the foundations of topology are something that are important to them, and I'm sure it all comes from Grothendieck being one of the first to say such things. So he wrote a famous letter in 1983 called Pursuing Stack to Daniel Quillen, and he sketched some ideas, but concluded for an algebraic axiomatic system for well-behaved topological spaces, but he concluded one seems caught in an infinite chain of Evia-Messier structures. He was basically trying to do high category theory. One is going to get hopelessly lost unless one discovers some simple guiding principle. So that's what I'm going to talk about. Now, in an instance of what we today call rubber ducking, right, where you tell your problems to a rubber duck, then the next day, somehow amazingly, you know the answer. After writing this letter to Dan Quillen saying the problem was too hard, he seemed to immediately solve it and wrote in the next day, I went on pondering, motivation does furnish a simple guiding principle in order not to get lost. So that's what we're going to look at. So his idea starts with n-dimensional balls. And we're going to represent them like this. So that's a 0-dimensional ball. It's a 1-dimensional ball. Just a little line segment. This is a 2-dimensional ball, which is just a disk. So the idea is there's 2 points, there's 2 paths, f and f prime, and a path of paths, alpha. So on, this is a 3-dimensional ball, and so on. Now we're going to use a bit more notation to refer to these guys. We're going to use lists to represent the entities that are in the neighborhood of these balls. So here we have an X, everything's going to have a type. And for points, the type is just going to be star, it means it's a point. So what do we have in the neighborhood of this D1? Well, we have X, we have X prime, and we have F, which goes from X to X prime. Excuse me, there's obviously a mistake there. In D2, what have we got? We got 5 entities, X, X prime, F, F prime, and alpha. And what have we got here? We've got 7 entities. So there's a clear pattern here, how we build up these neighborhoods of these balls. So we can represent them geometrically by thinking of them as geometrical balls, or we can represent them by thinking of the families of paths and paths of paths and so on, which we need to have around in order to comprise all the entities in the ball and its boundaries. Okay. And these lists, these are examples of little things called Computads. We're going to be talking more and more about Computads and more formally as the talk goes on. In essence, a Computad is a list of all the pieces that make up a space. It's the idea. So these are our first examples. Now, Grothendieck's idea started with the suggestion of gluing these balls together, forming what we call pasting schemes. So here's an example. We've got a 2-dimensional ball mu and a 2-dimensional ball nu and a 1-dimensional ball j, and they've been glued in this particular way. So there are some rules about how we're allowed to glue these pieces, these balls together. We can't do it arbitrarily. And the combinatorics are such that the allowed gluings correspond precisely to trees, okay, rooted trees. So these are sometimes called Batanin trees. We'll just call them trees. So let's see how this, so we have 3 perspectives on this single idea, which to me represents the sort of holy trinity, logic, geometry, computation. So here we have the geometrical perspective, right? These are literally the balls glued together. Here we have the logical perspective. This is a mathematical logical object, a tree. And here we have the computational perspective, right? This is a list that we can type into our computer and ask it to process. So you see how these 3 things encode the same idea. So here, for example, we've got a 2-dimensional ball mu, and here's mu, it's at height 2, right? 0, 1, 2. So we see that mu is 2-dimensional. Mu goes from F to G. And we see here, if we look on the left, we have F, and if we look on the right, we have G. And let's look at H here. If we go down on the left from H, we get X, and if we go down on the right from H, we get Y. So H is at height 1, and it goes from X to Y. And here we see indeed H is a 1 disk that goes from X to Y. So these pictures, if you're not sure exactly what sort of gluings are allowed of balls, the answer is it's just all finite trees. So we can also define the boundaries of these schemes, these pasting schemes. So these schemes are directed, and the positive boundary here goes X, H, Y, J, Z. So we call that del plus, and the source boundary is x, f, y, j, z, and we call that del minus. Okay, so these pasting schemes are really core algebraic entities for Grothendieck's idea. And then what he wanted to do is he wanted to understand how you can compose these balls together in the style of category theory or high category theory as it was then being developed. Okay, so here are his ideas. I'm just going to give them directly because they're quite simple and beautiful. So first of all, suppose we've got a pasting scheme gamma, right? So for example, gamma could be this guy. Then if you already know some way to compose its source boundary, call this U, and you already know some way to compose its target boundary, call that V, then you get a new way to compose gamma itself, which we call co-U comma V. And there's another related rule, which says that's a bit simpler actually. It says if you've got two distinct ways to compose the stuff in gamma, call it U and V, then you get a new way to compose the stuff in gamma called co-U comma V. So these guys, co-U comma V, they're always dimension 1 higher. And the idea is that in this case, co-U comma V is like a coherence law that says U is isomorphic to V. And here, this is like a bulk composite that says all the stuff in gamma can be composed in such a way that if you look at the source boundary, you see U, and at the target boundary, you see V. So it's kind of funny. It's saying if there's a bunch of stuff that you want to compose, you just have to decide how to compose the outside part. It's like a sort of holographic principle. It's a beautiful idea. It's not particularly obvious. So why does it work? It works because these schemes are geometrically contractible. So as long as you decide how you're going to compose on the boundaries, like nothing can go wrong somehow on the inside. So let's see a little picture. Here's a picture of gamma. Here's the source boundary. Here's a composite that we could choose, F composed with J. Here's the target boundary. Here's maybe a richer composite we could choose, H composed with, I use forward composition notation in this talk, H composed with J composed with the identity on Z. That should be straightforward enough. So we have a term by the first rule, which says we have a new way to compose all this stuff, all the stuff of gamma, by supplying a way to compose the source of gamma and a way to compose the target of gamma. And here's the resulting term. We just call it co, F compose J, brackets, H compose J, compose identity Z. Now, there are some extra conditions we have to check. I've been cheating a little bit. It's not really the case that we want to do this for any U and V. First of all, the given composites must be in the same Hom set. So this is globular high category theory, and U and V have to be parallel. So they have to already be in the same Hom set for us to be able to do this. We can check this here. F compose J goes from X to Z, and H compose J compose identity also goes from X to Z. So these guys are both in Hom X comma Z, so that was okay. Also, the given composites must be entire, so they must use all the variables of their domains. And again, we can check that because here we use H and J, and H and J contain X, Y, and Z in their boundaries. So here we're using everything from del plus, and here also we're using everything from del minus, so that's okay. We can't leave anything out. We have to, this really has to be a composite of everything here, not just some of it. And then Grothendieck's idea is that this gives the operations of the theory. This gives the composition rules of the theory. The actual composites themselves, you get by substituting, right? So if you like, these things are like abstract lambda terms. And then in order to have an actual, to actually incarnate them, you have to decide what you're going to apply them to, right? So geometrically, this Grothendieck scheme here tells us how to build all the new composition operations. And then once we've got a composition operation, we can apply it to any bunch of cells we like, as long as their sources and targets match up in the appropriate way. Okay. So it's a bit of a lightning tour. There's more fine details I could mention, but basically it's a simple, beautiful idea. And if there's something you're not sure about how it works, maybe there's probably only one reasonable way it could work. Okay, so let's rock through some examples. How do we compose f with g? Well, we do co x comma z, because we see x is in the source boundary of gamma, z is in the target boundary of gamma, so we have co x z, and we call this f composed with g. That's our standard notation. Suppose gamma is just this guy. Well, we could use the second rule and say sorry, but this gamma is snuck in. I've been a bit inconsistent with my notation. You can just ignore that. So we can have co x comma x. So right, x is entire over gamma and x is entire over gamma. So we can use this second rule. We've got a pair of gamma composites. We can write co x comma x. And this is more commonly known as the identity on x. Let's see another example. Gamma is the one disk. We're again going to use this second construction rule. The first term we're going to provide is the identity on x composed with f, and the second we'll provide is f itself. It satisfies all the side conditions. So this is something that says the identity on x composed with f is equivalent to f, so we normally call that lambda f, like the left uniter. Here's a fancier example. This is an associator. Now let's look at this example. Here we're trying to build something a bit like f inverse. So here we have to supply something over the source of gamma, and I've given y. And here we have to supply something over the target of gamma, and here I've given z. So in fact, that's a typo, but this is supposed to be a non-example, so it doesn't matter so much. The point is the source of gamma is x, so we definitely can't have a y in this slot. The source of the target of gamma is y, so we definitely can't have an x as I intended to write in that slot. So we can't do this. So there's no way to switch direction of cells. Actually, I'm corrupting history a bit. Grothendieck's original idea was for a theory of infinity groupoids, and it would have allowed this. So what I'm really presenting is a slight specialization that was introduced later by Maltsiniotis, which turns it into a theory of directed infinity categories. Here's another example. We can have co f comma f. The trouble here is that f itself is not entire over the whole of gamma. It totally ignores the g. So this is not allowed either. So basically you play around with this idea, and it seems kind of a crazy idea, but you play around with it and you find all the stuff you can build is just all the stuff that we know that we like having, like binary composites. Also you can have higher order composites, ternary composites, and so on. Identities, uniters, associators, right? They all come out very nicely. Now, Grothendieck's original letter was a bit ambiguous on a crucial point of how new terms are built from old ones, because clearly, right here, we're using binary composition. But this is how we built binary composition here. So this is like a machine that you have to do repeatedly. So first, you learn you can do binary composition, and then you can use it within another co-rule to build the associator, and so on, right? So these structures we're building have got a complicated internal structure. And Grothendieck's letter was a bit ambiguous about how we handled that. From a computer science perspective, or maybe a mathematics perspective, if you speak to the right mathematician, I guess there are some of them here, there's a clear answer, which is we do it by induction. Induction is the modern technique for building new structures from old ones in this sort of a crisp syntactic way. So let's remind ourselves about some important points regarding induction and recursion, and even something funny called induction recursion. So induction allows us to build sets from valid construction rules. See an example. So here are two construction rules. The first one says star is in S. So S is some set we're going to build, and star is an element that it contains. And here's the second rule. Given P in S, then f of P is in S. Okay, so these are two rules. And the idea with induction is we apply these rules however we like, however we can, to try to exhibit whatever elements of S we're able to. So let's see, well, star is certainly an S, but now we can apply the second rule. Given that star is in S, then f of star has to be an S, great. But now we have a new input to this rule. Given that f of star is in S, then f of star is in S, great, and so on. So that's it's easy to see that that's all the elements of S will be of this sort of a form. So what's recursion? Recursion is the principle that lets us define functions out of an inductive set. And it's super easy because every element of an inductive set was constructed in a very particular, unique way. For any element of this set, we know exactly how we built it, by what combination of these rules. It's never the case that we could have two distinct, it's never the case we can have two distinct elements of this set that were built in the same way from the same rules. Conversely, it's impossible to have one element of this set that we built in different ways from these rules, because the names of these elements just precisely encode the sequence of ways in which we applied these construction rules in the first place. So any element of this set, we know how we built it, and we can use this information to define a function out of this set, and that's recursion. So let's see an example. We can define a function j from this set S we built into the natural numbers like this. J of star is 0. And also given P and S, then J of f of P is defined to be J of P plus 1. And because P is somehow a smaller instance than f of P, we know that J of P will somehow already have been defined. So then J of star will be 0, J of f of star will be 1, J of f of star will be 2, and so on. So the reason this is nice is that inductive sets are somehow completely free and easy for computers to handle, right? We can just give them some rules how to build these sets, and the computers can go around and find every way to combine these rules together to exhibit elements. The computer doesn't have to use any, shall we say, creativity, right, in deciding, and these elements are supposed to be the same. We're not giving the computer some complicated rules to decide when some elements of the set are the same or whenever they're not the same. So inductive sets are the easiest sort of sets for computers to manipulate as part of a proof assistant. So now we're going to think about something called mutual induction. The idea here is that we've got multiple sets which we're trying to build simultaneously. See an example of that. So look at these rules. Star is in S. Given P in S, f of P is in S. Well, that's the same as before. But now we're also going to say, given P in S, G of P is in T. And given Q in T, H of Q is in S. So now we're constructing not only the set S, but also the set T. And this basically isn't any harder. You've just got two distinct sets you have to keep track of. And what you do is you keep turning the crank and you discover new elements of your sets and you add them to the list of elements you've found so far. And then you just keep applying these rules however you can. So star is in S, hence star is in S. G of star will be in T, and so on. Star is in S, f of star is in S, so that one's here, and so on. So that's not much different. So now this is kind of interesting now. Induction recursion is a funny idea as follows. The idea is that rather than first defining your inductive set and then defining your functionality with recursion, you're going to do it all simultaneously. And this turns out to allow some definitions which are really hard to handle otherwise. For example, consider these rules. Or again, J is going to go from S to N. So star is in S, we'll start with that. Given P in S, then f of P is also in S. Great, same as before. Now this one's a bit different. Given P in S, with J of P equal to 0, then G of P is in T. So it's like the same as, oh goodness me, what's that? So it's like the same as this rule, except we've added a little side condition that we have to check. Now you'll look at this and you'll say, well, what the hell's J? You haven't defined J yet. Worse, you haven't even defined S, which is the set on which J is supposed to be given. So that's just a feature of induction recursion, that you end up having to mention things before you seem sort of ready for them. And maybe that's why some people find induction recursion a little bit funny to think about, but it's not so bad really. Given Q in T, then H of Q is in S. So now what about J? We still haven't said anything how J is defined. Well, we just defined J by recursion as before. J of star is 0. J of f of P is defined in a certain way. J of H of Q is defined in a certain way. So this is just an ordinary recursive definition of J. The only thing that's weird about it is that we've already used it somehow above. So you could have said, well, maybe you could have just given these rules earlier. Well, that's true, but then we would be defining J before we'd even mentioned what S and T was. So it seems very peculiar to be defining a function before we've even defined its domain. So that's the intrinsic peculiarity of induction recursion. So because of this extra, this setup is similar to this previous setup, except we've got this extra side condition we have to check. And so we got fewer elements in our sets in this example. This might seem strange, as we've said, but in fact, there's a beautiful theorem from a few years ago by Hancock, McBride, Garni, Malatesta, and Altenkirch. And they showed that as long as everything is a set, that is, as opposed to a proper class or some higher order structure, then induction recursion doesn't actually give you any extra power. So any sets that you can define using induction recursion, you could already have defined them using ordinary induction, followed completely separately by a definition of your recursive functions. Now, you might have to be creative, well, not creative because they give an algorithm, but the point is induction recursion is still useful because the induction recursion could let you give a really efficient, compact definition, whereas the separately inductive and recursive definition might be a lot messier. And also, of course, not everything might be a set. You might be working with some proper classes, in which case induction recursion can be strictly more powerful. Okay, now we're going to play a game. Maybe coming to a TV set near you if this works out well. Let's see. I'm in discussion with a number of TV production companies. Whoops, it's the wrong way. The game is called Free Structures by Induction. Okay. So by the way, I like it when people ask me questions, so unmute yourself and just ask. I like if we have questions, maybe we have another discussion. That's fine, because maybe some of the stuff I'm saying seems a bit funny. Okay, so let's play this game. I don't have any theme music or anything, but let's imagine game show type environment. Okay, what's going on with this? For a chosen algebraic structure, can we build free examples inductively with structural functions given by recursion? Is this possible or not possible? So let's see what on earth I mean by this. So we'll start thinking about monoids. You can already see this is going to work really well on primetime TV, right? Let's press on. So consider the free monoid over a set S, A, B, C. Okay, so we all know what the free monoid means. So the free monoid on S will be an infinite, have an underlying set with an infinite number of elements. What are those elements? Well, we just look at the monoid axioms to work it out. Binary bracketed strings over the elements of S, for example. This is such a binary bracketed string. Oh, and also including this sort of null element identity, of course. And then we quotient that set by these relations. So the XYZ equals XYZ with these bracketings, and also we impose the unit law. So fine, I hope everybody agrees that's the definition of this set. So we generate it in some free way, and then we impose a quotient. The question is, this quotient set is what we really care about. Can we build it directly inductively instead of working with a set that's a quotient? Because working with quotients is kind of annoying. It'd be nice to be able to work with a set directly. And we win the game in this case. We can do it. So as we all know, a much more convenient way to work with elements of a free monoid is just to work with finite lists in ABC, where you ignore all the unit elements and you ignore all the brackets. Okay, so this is something that's really familiar to us as mathematicians, and I suspect we do this without thinking, right? I suspect last time you thought about a free monoid, it didn't occur to you to work with this set and quotient it. You just worked with the finite lists and didn't worry about it. Great. And it's also nice to notice that the monoid multiplication function is also then a recursive function, so it fits nicely into this picture. Okay, so let's crack on. Now, what about groups? Consider the free group over the same set S. So, of course, we know what that looks like. The underlying set is binary bracketed strings, but this time where we can allow inverses. So we can have B, but also the inverse. And when we quotient, we also quotient by the relation that says XX inverse is an identity. So can we build this quotient inductively? Lists don't work anymore, right? It's no good saying lists because we need this to be precisely the same element as this. So we can't have lists anymore. So for a while, I thought this was probably not possible. But then I was chatting with my student, Alex Rice, who worked out a nice way to do it. And also Fred Forsberg in Glasgow worked out a nice way to do this. And you can define an inductive type called lists, lists without adjacent inverse pairs. So the idea is that we have lists, but then when we try and compose those lists, we check if the tail of the first list is the inverse of the head of the second list. And if it is, we just delete those elements. And then in the end, we'll do this repeatedly until we find that the strings we're trying to concatenate, the last element of the first string is not the inverse of the first element of the second string, and then we just concatenate them. So for this, we have to do some tests, right? Like we have to test, is the last element of the first string equal to the inverse of the first element of the second string, things like this. So that's not part of induction, but it is part of induction recursion, because this test will be a function into the Booleans, and we have to define it recursively. And if we want that to involve that as part of the definition of the set itself, you have to use induction recursion. That's okay. And by this result that we just talked about, Hancock, McBride, Garney, Malatesta, Altenkirch, we then know that actually we could turn a crank and get rid of the induction recursion. It'd end up looking a lot more complicated, but we can, in the end, find some direct inductive way to describe the elements of the free group over a finite set. Fantastic. So we win the game in this case. Right. So now let's go up the hierarchy. Hey, Jacques, just answer your question, please, because I might not know. So just please.
Okay. Probably turn on my camera. You can do this in this case because you have decidable equality over the set S, ABC. But if you didn't, I think you have a problem. This doesn't actually work. You're assuming you can actually
absolutely
elements of your generating set have identity.
Yeah, thanks for pointing that out. That's definitely true. I'm going through these examples from a sort of classical mathematical perspective, but you're right, it wouldn't necessarily generalize. And of course, then with all these things, it's interesting to say, okay, can we do it in some loose, weaker logical setting with fewer assumptions? It would be interesting. Yeah, and I don't know the answer. Thanks for your question. Okay, so now let's imagine some fancier thing, monoidal categories. So we've done pretty well for these classical structures, right? Monoids groups. So let's go up in dimension. Consider the free monoidal category on some given objects and morphisms. By the way, we're just talking about free things. Nothing here about general monoids. We're just about free monoids. So what about the free monoidal category on some given objects and morphisms? Well, its set of objects will be, so there's a bunch of sets we have to build if we want to consider the free monoidal category, the set of objects, the Hom sets, and then we also have to define some functions recursively, the tensor product function on objects, the tensor product function on morphisms. Okay, so there's a bunch of stuff that we have to build. So what's the set of objects of a free monoidal category on some given objects and morphisms? Well, it's just bracketed strings in the generating objects. So that's fine, just like the monoid case. You can definitely do that. But its set of morphisms is the set of string diagrams, if you like, quotiented by homotopy. So here are some examples of some string diagrams. And the quotient that we do is a quotient by homotopy. I did some work with Antonin, who's here in the audience, I think, where we discovered these snails, and we proved a theorem saying that if you want a pair of morphisms in a monoidal category, which are homotopic, but as different as possible, then you get it from these snails. We proved a theorem about that. So you can see, actually, these are homotopic, although it looks like one is the reflection of the other, but also they are homotopic. You see, if you start at the top, we go down, up on the right, down on the left. And it's the same here. We start with this guy, and we go down, up on the right, and down on the left. So if you imagine having this made of rubber in front of you, you could bend it around and you could manipulate one into the other. In this case as well, it's clear that these two entities, these two string diagrams are homotopic. So for the theory of the monoidal categories, this is the quotient we're going to have to worry about, right? A much more complex quotient than what we were doing here, right? This quotient, and for the case of groups, we're handling this quotient. Now we're handling a quotient that's more geometrical. Maybe you don't like string diagrams and you want to think about things more classically. Well, that's fine. Alternatively, we could say the morphisms are expressions in the formal syntax of monoidal categories, so involving associators, unitors, and those sorts of algebraic generators. And then the quotient is then given by the equational constraints, which is the triangle and pentagon equations. Either way, it doesn't particularly help you. It's a huge set of possible expressions with a huge quotient. It seems hard to handle. So in this case, I really don't see any way that we could find some direct inductive construction of the quotient space. It seems really, really hard. Maybe someone has an idea. So now you might be thinking, well, yeah, it is hard. It's because you were trying to do something really dumb. Like, why on earth would you expect for interesting sorts of mathematical structures that you would be, there's all sorts of axioms which are very complicated. So why on earth would you expect to be able to construct direct inductive characterization of the quotient space? Well, one reason we might like it is because inductive structures are really easy to tell computers about. It's one way, right? We don't have to spend our time telling the computer how to handle the quotient space. But nonetheless, you might have thought this idea was doomed from the beginning. Okay, so we lose the game for monoidal categories. Maybe the problem was the weakness. Monoidal categories, well, they could be strict, they could be weak. Let's think about strict monoidal categories. Well, it doesn't help at all, because strict monoidal categories still have a bunch of equations, and we basically still have the same problem. So it's not really a problem about weakness versus strictness. Strict infinity categories, I mean, we also just completely lose, okay? So nothing's getting any easier, except weak infinity categories, we can win. And that's the whole point of this talk. Seems like this trick, this observation that free structures can be described inductively is something that maybe only works in low dimensions by some, accident of, the ubiquity of lists or something. But then the moment you go up in dimension, in particular to weak two categories, even monoidal categories are examples of weak two categories, seems that it completely goes. And indeed, for weak n categories, you lose. But when you go all the way to the weak infinity categories, you actually win. So in the sense that, so I think this is kind of interesting. It's a side point for the talk, but given some particular algebraic structure, I don't know, a field, a semi-ring, a monoidal category, a group, we're used to in the foundations of mathematics and logic, working with formal presentations of these structures. What is the mathematical property that lets us test if the structure does have this property that its free instances can be described in some inductive way? Maybe that's an interesting question, but maybe not. But it's at least not an obvious question. Okay, so obviously this perspective on weak infinity categories is going to be the main point of this talk. So now we're going to talk a bit more about these computads. So we've already seen some little examples of computads. So we saw these. We saw these balls, right? So the idea of a computad in this case is it tells you all the little ingredients. What are all the points and the paths of paths that you've got available? These are the things you've got available that maybe you could try to compose, and so on. So we're going to want to take that idea and apply it in higher dimensions. Okay, so an n computad is the generating data for a free n category. Let's see some examples, see how that works. A zero computad is a set. So a set is a zero category, and a set generates a set by just doing nothing. And I guess we're all comfortable with that. Okay, so what's a one computad? Well, a one computad should be generating data for a free one category. And so a one computad is a directed graph. That seems totally reasonable. But what data did we have to supply? Well, we had to supply an underlying zero computad V first, that's the vertices. And then we had to supply a set E of one-dimensional generators, the edges, F, G, H, J, K. And then for each edge, we had to give a source function and a target function, which relates it back to the lower dimensional structure. So obviously we're all familiar with that, but then we're going to start to generalize. So it's nice to see how this works. Okay. Now, given a one computad, of course, we can use it to generate the free one category. And then we could say, what are the syntactic composites that we can form? Well, there are a bunch of them. We could do G composed with J and so on. And we're going to write cell sub 1 of D for all of its one cells that we can compose, but in fact, just the syntactic one cells. So we're not quotienting here by associativity or anything like this. Worry about that separately. So this is our notation. Cell 1 of D means all of the syntactic one cells that we can build from this generating data, D. Then to actually build a one category, of course, we would then quotient by some axioms, associativity, and units. So now what about n equals 2? A 2 computad should be the generating data for a bicategory. So let's try to so what might that be like? Maybe not something we think about very often. So well, let's think about this. Well, a 1 computad had an underlying 0 computad. So it would make sense for a 2 computad to have an underlying 1 computad. Let's call it D, a directed graph. That'll be a good start. And then it should have a set G of 2-dimensional generators. So let's say it's the 2-element set mu and nu. And then we should have a pair of functions from G to the 1 cells of D, the underlying thing, saying for mu and nu separately, what's your source and what's your target? So just the same as here, except now we're going to have a globularity condition because we know threading through these ideas, we want to be doing globular high category theory. Other types of high category theory exist. We want to be doing globular high category theory. So we want these to be globular. So we want the constraint that the boundary, that if this is the source of mu, and this is the target of mu, then it better be the case the source of this guy is the source of this guy, and the target of this guy is the target of this guy. But other than that, anything goes. And the point of our, so, okay, I mean, these definitions, nothing very new or exciting about them. But so the main thing that we produce in our work is we generalize this to all n. So we give an explicit description as explicit as this for arbitrary n, and it works in just the same way, right? So just as a 2 plus a 2 computad involved a 1 computad and a set of 2 generators and source of target functions, this is precisely the same in our case. So we'll find that an n plus 1 computad is built by giving an underlying n computad a set of n plus 1 dimensional generators and source and target functions. And we're going to do this inductively. Okay, so that's why we've had this preamble, this warm-up about induction. In fact, we're going to use induction recursion because we're going to need to test side conditions, have little checks as we're going along. Those are defined in terms of side conditions. And the whole thing is going to be indexed. So we're going to do this at level 1, level 2, level 3. So that's the indexing. And we're defining a whole massive bunch of sets simultaneously. So it's all mutual. So overall, this is index mutual induction recursion. So what are we going to be defining? Well, we're going to be defining some categories, comp n, of n computads and n homomorphisms. So when I say we're defining these categories by index mutual induction recursion, what I mean is, well, this will have a set of objects. Or a large set, but I mean a set-like thing of objects, and we will build those sets by induction and induction recursion rather. So we'll have a set of objects and a set of morphisms. We'll build those by induction recursion. There'll then be some functions, like the composition function. It's kind of an important function on a category, and we'll define that by recursion. We're going to build some functors. So there's going to be a functor from the category of n computads, the category of n minus 1 computads, n positive, which gives the underlying n minus 1 computad. We're going to give it a functor into set, which for the n computad gives us a set of n cells. We're going to have a type functor from the category of n computads into sets, which gives the set of n types. That is the set of n-dimensional Hom sets. Right? So it's the set of pairs of n-dimensional cells which are parallel. That's the idea. So type is really just a small repackaging layer of a cell. So type is just a pair of cells which satisfy this globularity side condition. We're going to have some natural transformation as follows. So if you've got a cell, then that cell will be in some Hom set. And the source and target of that Hom set will be a dimension below. So if you think about that, that's natural to express as a natural transformation from the functor cell n to the composite of un, which takes you down to the lower dimensional cells, followed by type n. So this natural transformation tells you for each cell in the infinity category, in the n category generated by this n computad, what Hom set is it in? Apply the natural transformation, which acts like a function, and it tells you what Hom set it's in. So this is just exactly all the basic data that you need, right, in order to generate free infinity categories from some data. And there's a bit of additional data that we need. So remember that our first examples of computads were these. Our first examples of computads we had with these balls and also these pasting schemes, right? This is an example of a computad written in list form. So in particular, from any of these trees, we can produce a computad, and we need an inductive way to do that. But that's pretty straightforward. Those trees behave. Those trees behave pretty nicely. So that's what this is about. We don't need to look at that in much detail. So the idea here is that all the sets are indexed inductive recursive, and all the functions are recursive. So there's a lot of detail there. I don't think giving lots of detail is really great thing to do with a talk, so I'm not going to dive into all the detail, but we'll look at a little bit of detail. So first, let's look at a high-level view of this indexed inductive recursive structure. So first of all, there's a bunch of sets we have to define. We have to define the objects of the category comp n. That's some set, large set in general. We have to define the morphisms of comp n. That's another. That's more sets. The functor cell n has an object part. So we need to decide what those sets are. Right. So cell is a functor into set. So we need to decide what sets are going to be in the image. Type is a functor into set. So we have to decide what sets are in that image. So those are the 4 sets we have to build. We also have to build 3 functions. This is a function that says for any cell, what is its type? This is a function because it's the action on morphisms. So type is a functor into set, and we need to know how that acts on morphisms. Well, it's going to produce functions. So we have to build those functions. Similarly for more cell n is a functor into set. So the morphism part of that functor has to construct some functions. So we're going to better build them. And also this is the composition operation in the category comp n, which is the new category that we're building. We have to be able to compose morphisms of comp n, and that's a function. So here at each level n, there are 4 sets we need to define and 3 functions. And we, as I say, we define this in a big mutual indexed inductive recursive way, and so we can track the dependencies. So for example, to define the objects of the category of n+1 computads, for that we need to know what are the objects of the category of n computads, and if we go down here, we need to know how the type functor acts on objects, and we can see that here basically, because to define a 2 computad, we need to know what a 1 computad was, and we need to know all the possible types that our new generators can have, right? So this looks kind of complicated, but it's really not so bad, and it just shows you the connections between these guys. So now you'll notice there's a cycle here. When you're defining, so this is a recursive function, this is a recursive function. When you're defining recursive functions, if function f is defined by calling function g, and function g is defined by calling function f, you've potentially got a problem. It could be that this doesn't terminate. So when we discovered this, we were kind of worried. We thought, maybe this is the flaw. Maybe this is why you just can't do this, because it just doesn't work. But I haven't really got time to talk about it in this talk. I'm going to keep it to an hour. But it turns out that this is okay. And you could just make a direct argument, and you can see that in the definition of this function, we call this function, and in the definition of this function, we call this function, but always in such a way that it can never lead to an infinite sequence of calls. So any calls to these functions will always terminate to be well-defined, which is, of course, what we want. That means our recursion is well-founded. So that was something that really confused us for a long time. For a while, we were convinced, actually, that it was just clearly didn't work. Then we realized it did work. We thought, oh, what was wrong with us? That's how research often goes. So a lot of this project has been working out this complex dependency structure. And the only problematic instance is this little cycle here. We've checked carefully that that's okay. So let's look at a little bit of this definition in some more detail. So what are the objects of this category comp n+1? Well, there'll be triples, which we'll call n+1 computads, where C is an n computad. This is the underlying bit of the definition. V is some set of variables. And phi is a function from the set V to the set of possible types of the underlying computad. So the idea is we've got C. This is the generating data for a free n category. We want to produce the generating data for a free n+1 category. Okay, we're going to build on top of C. So we're going to have some set of variables. These are the new generators in dimension n+1. Well, those generators have to have some type. They have some source and target. And those types, there will be n types of C because of how Hom sets work, right? And to be honest, the rest of it pretty much follows the same pattern. I'm aware of time, and I'm not going to talk about all of this in detail. But for example, everything that I've written here on this slide really just comes from looking at what we did on this slide, right? n equals 0, n equals 1, n equals 2, and saying, well, okay, what could you plausibly say in the general case? Okay, now, the bit that's complicated, of course, is how do we define the cells? So we've got our computad, great, we've got our generating data for a free n category. Now, what are the actual cells of that n category? That is, what are all the ways we can compose this stuff up together? And that's where Grothendieck's ideas come in. And as we've already seen from the beginning, those ideas are sort of fundamentally inductive, right? That's what we were talking about. That's what we were talking about. That's what we were talking about here, right? Like if you've got a composite of the source boundary U and a composite of the target boundary V, then we get a new composite of the whole thing, and so on. So it looks amenable to induction, and that's why it works well in this setup. So there's a little bit of detail there about how we do that, and we can't take any credit for that because it really is just a direct reading of Grothendieck's idea for how this should go. And also, I don't want to give the impression that we are in this collaboration making a direct leap from Grothendieck's original work onto the results I'm presenting here. You know, things like this, for example, the notion that this has an inductive character has been mentioned by the people, and so on. So I don't have the time to go into full history, but I'm obviously jumping over some other related work. Although what's the main new contribution is this explicit indexed inductive definition. No one's ever given this explicitly before. That's the main new part, although this inductive character has certainly been known before, hasn't been packaged in that way. Okay, now let's talk about polynomial functors. I know lots of people here, Tim, David, many others like polynomial functors. So they've always been a bit of a blind spot for me, and I spent a couple of days reading about polynomial functors, and I think they're extremely beautiful. So let me explain, maybe I'm literally the only person who doesn't know anything about polynomial functors. I did it yesterday, and explain kind of what the idea is. Let's remember our simple mutually inductive definition from earlier. Star is in S. If P is in S, F of P is in T. And if Q is in T, then G of Q is in S. So that there's a really beautiful trick, which is you can take this sort of motley collection of rules and you can draw them in a picture in a really beautiful way. And it's just hit me yesterday why this is. You go online and you read about polynomial functors. Nobody just says this. Okay, this is what's going on. So I actually had to work this out somehow myself. Obviously, I don't take credit for the whole field of polynomial functors, but why did it take me 4 hours of reading? Anyway, okay. So star is in S. So we represent this like this. Star is in S. So we're drawing some of the graph here. Star is in S. Great. Now we want to say the following. If P is in S, then we can use F to put it in T. So look, P is in S, so we use F to put it in T. Great. Oh my goodness, sorry, that's jumping around a bit. Normally my LaTeX foo stops that sort of stuff. Now let's see. Q is in T, and G can put that in S again. Well, we use the same idea. Q is in T, so G can put it in S. So what we can see is that we've taken this data and we've drawn a picture of it. Seems like a sort of trick. It's not obvious that this trick generalizes or is particularly useful, but it turns out that it is. And if you think about it, what we've got here is a 2-element set here, a 2-element set here, a 3-element set here, and a 2-element set here. And we've got a function from this set to this set, and we've got a function from this set to this set, and we've got a function from this set to this set. So one function going left, and one function going right, and another function going right. And also this set is the same as this set. Sort of an important point. And such a triple is called a polynomial endofunctor, and you can read thousands of pages of literature by Joachim Koch, by David, by a bunch of people. It's a beautiful area that I'm looking forward to learning more about. So this is my question. Our definition is large. I believe our definition that we've given is large indexed inductive recursive. It's large because some of our constructors say you have to choose a set, right? So to build, so this is one of our inductive generation rules. We're building the objects of this category comp n. So what are your inputs? Well, you need an object. Sorry, we're building an object of comp n plus 1 inductively. So what are the ingredients? You need to pick from your orchard. You need to pick an object of comp n, one of the previously defined inductive sets. That's great. But then you need to pick a set V. You just pick it from the category of sets. It seems to me that whenever you have introduction rules like that in your inductive schema, then what you're doing is large induction rather than small induction. I could be wrong about that. It's also possible that I'm right about that it is large, but certainly not small sets that we're building. But it might just end up not mattering for a reason that I'm not expert enough to know. So the point is, if our induction recursion that we're doing in our definition was small, merely small induction recursion, then we could apply this theorem I mentioned earlier and use some black magic machinery to get rid of the induction recursion. So then it would just be an indexed inductive scheme, and we could certainly encode it as a polynomial functor. But here it's large, so we can't just turn this crank and turn it by application of an algorithm, turn it into a pure inductive scheme, so remove the induction recursion, thereby express it as a polynomial functor. Now, so a question I'd like to ask this community, maybe no more polynomial functors than me, is it possible to do this? To be honest, it feels to me like this is a sort of setting where it probably is possible to remove the induction recursion. I noticed that people are talking in the chat because I can see little numbers, but I can't access the chat. So just unmute yourself and say something.
So, sorry, one of the messages was from me, just pointing out the time.
Oh, great, thanks. So that really
I know that you haven't read that. Sorry, I should have.
That's all right. Well, I'm almost finished. Okay. Okay, so what else can we do? We can build a category of all Computads by taking a direct limit of these categories of n Computads. So we get a bona fide category comp, whose objects are Computads, which go up in all dimensions, and a particular Computad could have 0 generators, 1 generators, 2 generators, 3 generators, and so on for every natural number. We could also use this to define a general infinity category, not just a free one. I maybe won't focus too much on that. We basically leverage previously known ideas. Okay, now here's a really critical point, which will be my last substantial slide. So we saw earlier that we can describe the elements of a free monoid inductively. Okay, that was one of our first examples. But I said at the time, obviously not every monoid is free, so a lot of the time we work with monoids that aren't free, so maybe we care a bit less about this than we would. Same with groups, right? We can describe the elements of a free group inductively, but not every group is free. Now, we've also seen, of course, the main point of this talk, that the cells of a free infinity category can be described inductively. And it's certainly the case that not every infinity category is free. But every infinity category is equivalent to a free infinity category, right? It's profoundly not true for monoids. It's not true that every monoid is a free monoid. It's also not true that every monoid is isomorphic to a free monoid. Just not true, and not really interesting to think about. But because of the magic of high category theory, every infinity category is equivalent, weakly equivalent to a free one. Whoops. So in some sense, comp, this category that we build of computads and computed homomorphisms, okay, it only really can tell you about the free infinity categories, but every infinity category is equivalent to a free one. So actually comp represents and is in some sense as good as the entire theory of infinity categories itself. It somehow relieves you from the need of ever needing to talk about any non-free infinity categories. There's an adjunction, as you might expect. So from any computad, we can generate the free infinity category on that computad. And also every infinity category, we can build a computad from it, where basically every single cell of the infinity category becomes one of the generators. And that's sort of how this equivalence works. And then what we see is that comp is kind of then, infinity cat obviously contains all infinity categories. Comp certainly does not contain the free ones, but every infinity category is equivalent to a free one. So comp is kind of like a better behaved version of infinity cat, which is somehow algebraically sufficient for many purposes. Now, a lot of the stuff I've said, particularly on this slide, is already known. Particularly Richard Garner's got a really wonderful advances paper on N Computads, where he does a lot of stuff, and a lot of the stuff I've said in his talk has come from him. What he does in that paper is very general. So his results aren't just about, say, globular Grothendieck style infinity categories. They apply to all sorts of approaches to infinity category theory. So what he certainly does not do is give an explicit inductive description of what it actually means to work with these n computads for the globular Grothendieck style case. So that's our contribution. But then it's nice that we see that it fits in. So it's exactly a model of computads in Richard Garner's style, and all the theorems that he proves about them. We can also prove those theorems, but more directly with respect to our particular structure. So we feel like what we've come up with is sort of the example that's kind of been missing. It's like the canonical example of these computads which people have studied. So for example, this was known abstractly that every infinity category should be equivalent to a free one. It comes out, and this cofibrant replacement, this is well known by Richard Garner, but we can sort of exhibit it more directly and succinctly. Okay, so that's the end of my talk. Free infinity categories can be constructed via indexed induction recursion. Since every infinity category is equivalent to a free one, these computads in some sense give a universal model for infinity categories. Somehow it's enough if you know about this particular, it's a sort of a complicated one, but if you're happy working with this particular inductive structure, then somehow you've got the whole of infinity category theory to play with. More or less, I mean, you can sort of read Grothendieck's original letter and sort of see this there, if you ask me. Further interesting things that we can't yet answer. What free algebraic structures miss inductive presentations? Is there some algebraic property we can use to determine this? Can the induction recursion be removed in this case, giving a polynomial functor? That would be really fantastic. And what about other models, cubical and so on, work in progress? And a fourth thing, which is pretty cool, but I don't have a bullet point for it, so I forgot. So previously, before this, we did this work, Eric Finster, Simon Mimram described a type theory for Grothendieck infinity categories. And type theories are also inductive in their structure. So the fact that our theory is inductive sort of matches the fact that theirs is inductive. But our setup has got particularly a lot of extra power because they work in a type theory. They could only have finite sets of generators and variables because everything's finite in type theory. We don't have that problem at all. We had to do a lot of work to get around that. But basically what we've done is we've taken something that's already done in the world of type theory and we've lifted it to reincarnate it as computads. So we don't say, here's a list of free variables. We say, here's a set of variables, things like this. And our sets don't have to be subsets of some previously specified pre-given list of variables and so on. So the other thing that we wonder is, to what extent can this be done for any type theory? Can you take some type theory and computadify it, turn it into an inductive structure more in this style, where in particular that would liberate you from only being able to work with finite context? Okay, that's the end of my talk. Thanks very much.
Thank you very much, Jamie. That was a lovely talk. Feel free, people, to unmute yourselves and clap, or virtually Zoom clap, or whatever best suits you. We will move over. Maybe we'll only have 1 or 2 questions before we end the live stream. We're a little bit over time, but does anybody? Oh, there's already a hand up. So Andre, would you like to ask your question?
Yes, I can see. Hi, Jamie. Thank you very much. Listen, I think your examples with the monoid and groups were finitely generated, right? And if I understood correctly, this infinity category is not finitely generated, right? So you need infinite set of generated.
Some infinity categories will be finitely generated, but many infinity categories will have no finite generation. Yeah.
Yeah. But
you could certainly have a finite infinity category. For example, let's go to here. We could generate an infinity category just from one point. Then we'll have the identity on that. The identity, we can compose that identity with itself. We'll have an infinite number of we'll have an infinite number of 1 cells, an infinite number of 2 cells.
Okay. So you don't assume you have a set generation for each k, for each level. So it
yes, we do, but
okay.
Right, because we take this direct limit, and to the point. Well, what's the best slide? So when we do this, right? When you have a directed graph would have no edges. It's no problem. It's just the same.
Okay. No. The reason behind was that if it's infinitely generated, I think it should look very differently. So in that case,
these are. But that's precisely what I'm saying, though. Our Computads can be infinitely generated, and that fits perfectly well in our scheme. That's what we claim.
But would you? But also, if I followed correctly, you cannot still reduce it to inductive, right? So you have this inductive recursive, which is kind of
so I've conjectured. I can at the end of the talk, I conjectured that we can, but no, at the moment we can't. Yeah, we don't know how to do that. Would it surprise you if we could do that? Or?
Because I kind of imagine in finite case, right? You can do induction first and recursive after, but if it's infinite, somehow my intuition is that it would.
Yeah, well, I feel it would work out, but it's fair enough. We haven't managed to do that yet.
Thank you.
Thanks for asking.
Hey, Valeria, you had your hand up next. Would you like to ask?
Hi, Jamie. That was lovely. I really enjoyed kind of being taken via easy examples through the whole thought of how to. I mean, I always look at things like Computads and no, this is too hard. No, not going to check it. But I have a kind of very unrelated questions to some extent. So when you say that in Grothendieck's letter, he talked about this business of things being entire, kind of using completely what is given. I mean, it kind of gives me the impression of something a little bit like linearity, right? Because, you're not allowed to forget stuff. I think there's no mention that things could not be repeated, but there's this mention that you cannot not use something that's being presented, right? Is that correct?
Yes, that's exactly right. And you have to use everything exactly once because of the structure of these guys. I mean, we couldn't. It sort of flows from left to right. So if we want to have some entire composite, for example, if we try to do H composed with J composed with H again, I mean, that would be impossible because of how it's arranged. So not only everything has
so it's totally linear
exactly once. Yes, that's true. There is exactly a linearity behavior.
Excellent. So, kind of there's another handle for me to think more about it. Kind of. So thank you. That's nice.
I had my hand raised next, so I'm going to ask my own question myself. So what's surprising to me well, lots of things are surprising. Like, maybe this isn't surprising, but if it isn't, can you tell me why? So it's surprising to me that you can end up with infinity categories by like the stuff you construct. I think it's on slide 13, if you want to skip to it, maybe not. Like you make some categories, you have some functors, and you have some natural transformations. And this lets you do the whole theory. So what would happen, say, for example, if like I went one level higher and I said, I'm allowed, morphisms between my natural transformations, and everything I originally asked to hold on the nose, I now ask for it to hold up to these higher. Like, is there a good reason why stopping at like the 2 categorical level is somehow enough? And what would happen if you go further? Would it give you nothing more, or like?
Yeah, that's a good question. So one thing that we can, one thing that we completely miss, that we can completely not do at all, is so these comp n, the objects are n Computads, the morphisms are basically functors of n Computads, but there should also be something like a natural transformation of functors of n Computads and so on. And we can't describe any of those. It's completely outside this technology. Doing that is very, very, very difficult. It's something we thought about. We're not missing anything in the sense that, I mean, we do really build genuine weak infinity categories with nothing missing. It's just, we can talk about those infinity categories. We can talk about the functors between them, but we can't talk about the natural transformations or anything like that. It's kind of annoying, but it's not wrong, but it just means there's certainly more that can be done to get access to that structure. Another thing maybe you could be asking is, why, to do this, did we need to use 1 categories? Why not 0 categories or 2 categories? I don't have a good answer to that. Ioannis, do you have an idea? Ioannis is one of my collaborators who's here.
He shook his head. Oh.
Sorry. I mean, I don't know what we would get with like if we use 2 categories here, but I can't imagine what interesting 2 morphisms between the natural transformations that we're using we could have, honestly. I don't really know.
But it is funny, Ioannis. I mean, I agree with what Tim's saying, right? But...
I do have a comment though on the previous thing that you said about size. So we know that if we pick all the sets in that we had before to start to live in some universe U, then all the categories that we define are locally U small, and all the functors land in those small sets as well. So maybe if we do some restriction like that, we could try to have some information. I'm not sure if that's of interest, some inductive.
Yeah, thank you. So our definition is large. So I've called our definition here large inductive recursive. It could definitely be worse. It's easy to give inductive recursive definitions, which climb rapidly up the hierarchy of universes into the stratosphere, right? And then you're completely, and that was actually what induction recursion was designed for, to let you be able to do that in a powerful way and build universe types. We're not doing that. We stay at whatever universe level we want to be at, but the point is we can't just work with small sets. And I don't know to what extent that breaks, because all I've done, I'm afraid, is read the introductions of these papers that talk about taking an inductive recursive scheme and turning it into an inductive scheme. And what they say is, if everything's a set, you're fine. Otherwise, you're not fine, right? And what we need to do is actually read those papers or talk to an expert. I haven't seen an example, because those people, the people who work in the field of induction recursion, think about this, they really care a lot about these powerful inductive recursive universe definitions that zoom into the stratosphere, up the universe hierarchy, because that's what induction recursion was designed for. So they've really got these in mind. It might not have occurred to them that anyone's particularly interested in a large inductive recursive definition like this, which is at some non-trivial universe level but stays there. So that's sort of one of the reasons why I do have some hope that that we can do this and then get a polynomial functor for infinity category.
Okay, I think what it's a good idea now is to end the recording and end the live streaming service, and if you're happy to stick around for a bit more, Jamie, maybe we could have some more offline discussion or whatever with people. So if we would all like to thank Jamie again for a lovely talk.
Thanks everybody, really nice audience. Thanks, I really enjoyed it.
and I will end the recording and live stream.